Sorry? I can ask my mom whether she wants to join if you want. Is this okay? Should I put it closer to my mouth? Not gonna glow. Well, I should leave it there because then it's gonna glow more.
Hi, everyone. Congrats to every one of you who made it here today. It's freezing cold. Glad that you're still moving. So today we have Professor, right?
Not yet.
Okay.
Soon to be
Dr. Chiara Spinello from University of Oxford to give us a talk, which looks interesting. And we'll soon find out what it's about. So previously she has taken a bachelor in physics and master in astrophysics and space science degrees at the Federico II University of Naples. I pronounced that correctly, right?
Amazingly good.
And then
Well
she
done.
went on to Captain Astronomical Institute in Groningen in the Netherlands for her PhD. And then went to Max Planck Institute for Astrophysics in Garching, Germany, as an independent research fellow. And then she ended up in Oxford since 2020, and now she's here today with us. So I'll hand over to.
Thanks, Yinchen, and thank you guys for inviting me. This is actually a great pleasure, and I will be sort of bring you to a journey that has to do with how do today giant elliptical galaxies form, and how can we use relics, which are the fossil record of the very first galaxies that are assembled in the universe, in order to constrain the structure formation of the most massive galaxies of the universe. And why this beautiful picture of me as an archaeologist? Because this is essentially what I do. I work as an archaeologist finding those fossils. I'll show you what they are, and I'll explain you why I'm calling them fossils. And I use them as a complementary method to investigate on the very early phase of galaxy formation in the universe, then JWST, observing galaxies at very, very high redshift, so very far away in space. Those guys here are actually local. They are nearby, behind the corner, but they still contain the oldest star in the universe. So if we're lucky enough to find them and we characterize the stellar population, so the stars that compose them, then we can put constraints on the very early phase of structure formation, but with the ease of being in the local universe, which is easy from many perspectives. Okay, so this is the outline of my talk. I'll start with sort of putting everybody on the same page with a historical overview, explaining you what is a galaxy today and what was a galaxy at the beginning of our century. And then I'll give you an outline of the most established or the accepted models for galaxy formation, focusing then in particular on the most massive galaxies, which are giant ellipticals. And by the way, why do we care about them? Because they contain overall more than half of the entire mass of the universe, and they are responsible for its chemical enrichment. And when you talk to an astrophysicist, when you talk about metals, when you talk about chemical enrichment, you're talking about everything that is not hydrogen. So we're cheating big time here. For us, metals is everything that is not hydrogen, and this is what I mean by chemical enrichment. So forming all the elements that are not hydrogen. And how do they evolve across cosmic time? And the big question that I'm trying to answer with my research and with relics is whether or not star formation works always the same across different cosmic epochs. So assuming you're observing a far away galaxy, the very further away you can find, and you're observing a similar galaxy today, did they form stars in the same way? Did they went through the same physical processes and mechanisms for structure formation? The answer is not. But it took me 50 years. Well, it took us 50 years to realize that. And it's just about 5 years that we finally know that star formation changes with cosmic time. Okay, so what is a galaxy? Back in the 1900s, galaxies were found to be fuzzy objects on the sky, both with small telescopes and with naked eyes, because back in the time there was not light pollution, so the sky must have been amazing. There were those, you know, fuzzy things with a bit of a spiral behavior, but nobody really knew what they were. Nobody really was able to observe them in the great details, and I promise you I'll show you prettier picture than those. Nobody knew what they were made of, and the hottest topic was whether or not those objects were external to our Milky Way or they were internal to the Milky Way. And in 1920, at the Smithsonian Museum of Natural History, two scientists got together in order to start what is then being called a great debate. So there was on one side Herbert Curtis, believing that nebula were indeed big collection of stars outside our own Milky Way. And there was on the other side Harlow Shapley, claiming instead that they were contained in the Milky Way. And this was question that had huge implications back in the time, because they were still not sure how big the universe as a whole was. So Shapley actually thought that the universe, the Milky Way, was making up the entire universe and there was nothing else. Whereas Curtis was claiming that those systems were external, and he was even attempting to measuring distances, which were completely wrong. But yeah, they came together, they discussed, each one of them discussed their technical papers, and then they had a joint discussion in the evening. They fought, they could not reach an agreement. There was no way to reconcile those two theories. That kept existing for another 3 years, when finally Hubble came and settled it once and for all. How did they do that? He was working at Mount Wilson at the time, operating this small telescope, and he was observing in particular the Andromeda galaxy, one of these fuzzy spiral nebula on the sky. And one night he got super excited because he found a luminous spot in his photographic plate. And this luminous spot was not present in all the previous images that he had taken of the same galaxy in the same patch of the sky. And this spot, he immediately wrote, because he was so excited, VAR on the photographic plate itself. VAR stands for variable stars. And he immediately identified that as Cepheids variable stars, and those are today called standard candles. So they are important objects that allow us to estimate distance with, you know, fair precision. So Hubble could estimate the distance of that star that was in the Andromeda, and because the distance was extending further than the Milky Way, it could finally establish that galaxies were external objects, collection of stars. But how do we measure distance? In order to let you understand why we can measure distance, we have to pass through the slide that explains how do we measure luminosity. I told you that variable stars, Cepheids, are standard candles. Now imagine you have a candle or any source of light of which you know the intrinsic luminosity, and you observe it here in front of your eyes. Then you bring it further away from you, and then you keep moving and bringing this source of light further and further away. Obviously, the apparent luminosity will, you know, the luminosity will decrease by moving this object away. And through simply, strictly geometrical relationship, we see that this is an inverse square law, because obviously you scaling with the area, with the surface. Okay, so you move twice as distance as you were, and your factor, you were getting 16 photons, and you knew it, and now you get 4 photons because you divide by 4, and so on and so forth. So assume that you know the intrinsic luminosity of this object, and you measure the apparent luminosity of that object at a different distance. Then you can estimate from the difference between the apparent and the absolute, you can simply estimate the distance. We astronomers are weird people. We like logarithmic scales that go upside down. So we have this magnitude system. I don't want to go into too many details, but basically we use as absolute magnitude the brightness that an object will have at a certain distance, which is 32.6 light years. Do not ask me how much is a light year. We do not use light years in the extragalactic astronomy community. We should use so big numbers that will get crazy. I'll show you in a second what we use instead. But yeah, you take the object, you put it at the distance of 32.6 light year, and you call that the absolute magnitude. Then you measure through your telescope the apparent magnitude that the object will have at any given distance you're observing. So appear to the observer, measure at the telescope. You do one minus the other, and well, you scale it through this inverse power law, and you automatically get the distance with this formula, where capital M is the absolute and small m is the apparent. Okay? Take-home message is, if I know the absolute magnitude of a given object, I can measure the apparent magnitude through the telescope. I can estimate distance. Now, the next question is, how do I know the absolute magnitude of a Cepheid, of a variable star? Well, that comes thanks to the great results achieved by Henrietta Leavitt, again at the beginning of the 19th century. She discovered that Cepheids are indeed variable stars, so they will have a period. They will blink on the sky, they will reach the maximum, get dimmer and dimmer, reach the minimum, and then gets brighter and brighter again until the next maxima. The difference between two maxima will be a period, and she discovered that Cepheids with longer periods are intrinsically more luminous than those with shorter periods, and she could sort of trace the period luminosity relation. So once you are able to measure the period through light curve, so you follow the stars, you observe the star in different time, then you can measure the luminosity. If you know the intrinsic luminosity, then you measure the apparent one through the telescope, as Hubble did at Wilson, and you get the distance. It sounds very complicated and convoluted, but this is actually the simplest and perhaps one of the best ways to measure distances in astrophysics using standard candles. And by the way, this has been done with supernovae. And in 2017, the Nobel Prize was assigned to 3 scientists that discovered through supernovae expansion, through measuring, through redoing the same process with supernovae stars, that the universe was accelerating. All right, Hubble didn't stop there, but he also discovered that our universe is expanding and galaxies are going away from us at a speed that is proportional to their distance. So this is often called the Hubble constant, and it's a sort of a rate of the expansion of the universe and relates the velocity to the distance. And oftentimes, you might have seen it already, there's a possible comparison between our 3D universe and the 3D raisin bread. So imagine to prepare a raisin bread, and you measure the distance between any pairs of raisins. Then you let it stay for a couple of hours, it grows, and therefore every single measurement, every single distance between a random pair of raisins will increase. Okay, it's just pumping up in all dimensions. And this is roughly what is happening to our universe. There's no reference point, everything is expanding, and therefore everything is moving away from everything else. And I need to show you my personal model of the universe. This is instead in 1D, and I didn't invent it, but I stole it from Joe Dunkley of the University of Princeton. Imagine to live on the string. Imagine we are living in a 1D universe, and please imagine that the string is extending left and right infinitely. Okay? So when the universe expands, every single star is going apart. The distance between any given star is increasing. And if you are, for instance, this star here, the second one, you see this one separating by a given amount, but you see this one separating way more from you. Okay, so the further away a galaxy is, the quicker it's moving away from us. This was a great discovery that sort of allowed people to open up a huge field of research, and we sort of started to wonder whether or not we could actually measure velocity with some light quality, in a sense. And the answer is yes, we can. We look at the electromagnetic spectrum and we identify lines. We take the sun as our reference, and this is the optical spectrum, for instance, and here you have a sodium line, which is absorbed at 5900 angstrom, just to give you a number that I remember on the top of my head. And then, you know, through the Doppler effect, that if an object is coming towards you, then the lines will move towards the blue of the electromagnetic spectrum, whereas if the object is receding, so it's going away from you, then the light will move, the absorption on emission lines will move to the red. Okay, so if the objects are going away, everything in the electromagnetic spectrum will move to larger wavelength, to the red. And this has allowed us to come up with a sort of recipe to measure, to use another quantity, which is way better than light years, and we call it indeed redshift. If you take your reference lambda and you measure the delta lambda, so how much it has been moved because the object is going far away. So let's assume that sodium was at 5900 and you measure at 6100, this is 200. This is your delta lambda. The reference was 5900. You just take the ratio between these two measurements and you get a number that we call the redshift. And first approximation, because of the Hubble expansion law, this is velocity of the objects divided the speed of light, which is a constant of nature. Okay, so we can measure velocity if we know the redshift. So if we have access to the electromagnetic spectrum, we can measure the redshift if we know the velocity, and you know, one or the other. So we can now sort of understand that, in a sense, the light needs time to travel until us. That means that actually looking further away, I already said a couple of times that people with JWST or nowadays were looking for the further away galaxy. Why are we doing that? Because the further away you look, the more in the past you're looking. Because the light has to take time to travel to us. Okay, so the redder you go in redshift, the higher your redshift is, the further away in space you're going, the more separation there is between you and the very last of the stars, the more you're going to observe in the past. Another practical example, take a picture of you with those clothes, with this haircut, and then walk until Australia. You're really good in shape, you're young, you don't want to take planes, you just want to walk and then swing. It's going to take you forever, let's say 10 years. But you know, you're still young, you're really enthusiastic, you really want to see kangaroos, so you're willing to do that. You take the picture with you, you walk, you swim, takes you 10 years, you arrive after 10 years and you look completely devastated. Like long hair, beard, and the clothes are completely destroyed, you're wet. You go to a fellow, you show the picture of you, they see a completely different picture, right? You were all fresh and relaxed. This is exactly what it's happening when we take the light out of a cosmological extragalactic object. We observe the galaxy. It takes a long time for the light emitted from the galaxy to arrive until us. And we see the galaxy as she left to go to Australia, but the galaxy is now completely devastated. And many, many times, while the light is traveling, many of the stars that were originally populating that galaxy have died already. So, you know, we have to take into account the time dimension in everything we do in astrophysics, and especially in extragalactic cosmology. Okay, this being said, let's sort of close this parenthesis, this is historical parenthesis, and let's try to look at some pretty picture. Today, obviously, we made a lot of progresses in the field, and we now know that galaxies are huge collections of gas, dust, stars, and their solar planets, solar systems, and they held together by gravity. Okay, this is a beautiful picture that I took from the JWST, from one of the many JWST James Webb Telescope press releases. And here you see a plethora of different shapes, different colors, different galaxies. Some of them are really, really far away. Some of them are close by. They all look different and they all look amazing. So if I zoom in, Hubble already sort of classified galaxies in 3 broad families, and I'm sure you're very familiar with that. Spiral galaxies, they are surrounded by beautiful spiral of gas. Gas is the fuel for star formation. So whenever there's a lot of gas, it's probable that new stars would be formed. They tend to be blue, and I'll tell you why in a few minutes. And they can range in mass. They can be dwarf, so they can contain, say, 10 to the 8, 10 to the 9 solar masses, or they can be a bit bigger, like the Milky Way, up to 10 to the 11 solar masses, so they're pretty heavy. But the heaviest and biggest one are ellipticals. I already told you that they make up for more than half of the mass of the entire universe. They are giant blob, so they ellipses on the sky, and they don't have that much gas surrounded them, and they are, we say that they are less rotation dominated. So they have a huge potential well, and the motion tends to be more chaotic. The motion of the stars within ellipticals tend to be more chaotic, and they tend to be bigger, although there are also dwarf ellipticals. And then everything else, Hubble called it irregular, because he could not classify them in one or the other class. And Hubble also hinted for a sort of evolutionary picture, with the ellipticals being the early type galaxies, so the ones that came first. But this is not well documented, so we don't really know whether Hubble really meant to draw an evolutionary picture. And yeah, more pretty picture. Hubble Space Telescope allowed us to observe amazing details like disk, dust lanes, beautiful spiral arms, ring around galaxies, and then so on and so forth. And Hubble was observing in the optical wavelength, whereas JWST, that was launched maybe 3 years ago, observed in the infrared. So again, remember, going redder means going further away, and that allowed us to have a complementary, still very beautiful view of galaxies. We started to observe the very first galaxies in the universe, thanks to JWST. But I'll claim there's another way to do that. Okay, pretty picture, pretty galaxy, everything is beautiful, but how do actually galaxies form? There are 2 main theories to explain galaxy formation in the universe. The one on the left is the top-down, or also called monolithical collapse. We start always with a cloud of gas and dark matter that starts to collapse. And then at some point, we reach a critical density that allows stars to be formed. But according to the monolithic collapse, we form a single massive disk shape, so rotationally dominated structure. And this is actually not that supported by observation. Whereas what we believe is the right model is actually, well, as I said, it's not really supported by observation, but we really, we prefer nowadays the hierarchical structure formation model that sees the same cloud of gas and dark matter collapsing because of gravity, but then small structures form first, and then they merge, interacting because of gravity, and they form larger and larger structures as time evolves. And today we've been very successful in simulating the entire universe with a supercomputer. There's many hydrodynamical, cosmological simulation build up with this hierarchical galaxy formation model. And I sort of have taken 2 videos from the Illustris TNG simulation, simulating the formation of a spiral galaxy. You'll see very soon it appearing here, and a massive elliptical. And here you have this redshift going down. That means that we are approaching the local universe. So we are evolving, we are following those galaxies in times. And so you see small blobs getting together, orbiting around each other until they merge completely. And now in a while, you should start seeing differences between the 2 panels. Here you see already a bit of, spiral structures forming, whereas here you don't see any. And there we are. We end up having a beautiful spiral on the left, and we start having something that looks like a elliptical on the right. The mass of the object is similar, but the rate at which star gets formed, new star gets formed, is much smaller in the elliptical. And yeah, I think we're almost done. You still see some bullet going down and then getting recatched. Voila. Okay, so I told you, so far the story checks out, right? We believe that structures are forming hierarchically. We believe that the small ones are then merging together to form the bigger ones. Everything seems to be okay. The computers are really successful in simulating the entire universe. All good so far. There's a big problem though. We sort of know how to measure ages of galaxies, although we should reflect on what is the age of a galaxy. But we can sort of measure how old the overall population of a galaxy is. And if we do that, we discover that early type or elliptical galaxies, especially the very massive ones, contain the older stars. But if they are the end product of the hierarchical formation assembly, how can they be the oldest? There's something, there's something that we should explain to ourselves. If they're the end product, they should have the younger stars. How comes that they are the end product and they're the older? Well, in order to reconcile that, and especially for massive galaxies, astrophysicists come up with what is called the two-phase hierarchical formation scenario, which sees a first phase, which occurs very, very early on in time when the universe is very young. Everything starts with a Big Bang, and then dark matter particles are starting to collapse in our cloud of gas, and then the density reaches a critical value, and we can form the first stars. And we believe that the first stars are formed through starburst. Those are incredibly energetic, super quick star formation episodes, able to form 10 to the 11 solar masses in a very short time. But then what happens is that the gas gets consumed, in a sense. So the fuel to form new stars starts to lag, and then we end up having nothing to form star with, and then the star formation quenches. If the star formation quenches, the population starts to age, and then we end up roughly at redshift 2, but honestly with JWST now we know that it's redshift 4 to 5, so very, very early in time when the universe was really young and dense, we end up having what we call a red nugget. This is an object that is incredibly ultra compact, but yet very massive. It could be much more massive than our Milky Way, having size 5 times smaller and without any gas surrounding it. And then what happened next is a second, much more time extended phase, which is characterized by a lot of mergers and interactions between different systems. We saw that in the hydrodynamical simulations. Smaller systems get attracted by gravity from these incredibly dense objects. They merge together, and during this phase, we form new stars, and there's a size growth. So we end up with the red nuggets transforming itself into a local giant elliptical. And depending on the kind of merger, we can have this incredibly dense nucleus stay, say, untouched within the local giant elliptical. It can be completely destroyed in the process. But nevertheless, even if it stays untouched, the stars populating the nucleus get contaminated by new stars that are falling in, or gas that it's then forming new stars in. So what I'm trying to say is that when we observe local giant ellipticals, we're observing a collection of different stars that have been formed through different processes in different cosmic epoch. So it's really important, in a sense, to go as back as possible on this line, and that's why JWST was really transformational in this context, because the more you go back, the more you approach the early universe, the more you can investigate on the very early phase of structure formation in the universe. However, mergers and interactions are a fully stochastical process. That means that our simulations do predict that a tiny percentage of those red nuggets in the early universe should evolve completely untouched, without meeting any other structure, any other galaxy in the universe, without gaining any fuel to form new stars. And so they should arrive until the present day universe as ultra compact and massive as they were, populated by only the oldest stars, only pristine stellar populations that were formed when the universe was very, very young. So if we're lucky and smart enough to find those treasures, then we can play the archaeologist game. Okay? This is exactly what I've been doing in the last couple of years. I've been inspecting huge patches in the skies, looking for those objects, the fossic relics of the ancient universe, and I've been using them in order to constrain the mechanisms of star formation in the very early universe. But I did that in the local universe, where a 4-meter telescope is enough to get incredibly good signal on those objects. Whereas if you really want to observe at high redshift, further away, you either need a very big telescope, you're restricting to the brightest objects, so you have a bias in your selection, or you go to space, which is incredibly expensive. Okay, how do we find relics? Spoiler alert, I did find them, and they're even more numerous than we thought, but it was a journey. It was incredibly difficult. We started off with millions of galaxies observed throughout the sky, and we selected the one that looked ultra compact. How did we do that? Well, we know how to measure the stellar mass of an object, and we know how to measure the radius, although there's many different definitions of what is the radius, where does the galaxy start and where does the galaxy end. We use the effective radius, which is the radius that encapsulates half of the total light of a galaxy. But it's just a convention. And we selected the objects that were sort of scattered in these relations. So they were the denser ones and the most compact ones. But then we needed to make sure that they were actually galaxies. Because, when you have ground-based observations, the Earth atmosphere can really screw up your data, and the atmosphere can sort of blur up the image, and even a star can look like an ultra-compact massive galaxy. For that, we used colors. We don't do that manually. We use machine learning techniques. But basically, we observe the galaxy through filters, broadband filters, and then we take one filter minus the other. And because galaxies are a collection of stars, and stars are, in first approximation, black body, they radiate as a black body, by looking at the sort of the peak of the distribution, the hotter the star will be, the bluer the peak of the distribution will be. And if you take two filters, to measure this black body variation, and you take the difference between the two filters, you can sort of measure temperature, roughly. And by measuring, by plotting colors versus colors, then you can sort of separate stars, quasi-stellar objects, and galaxies. So we pick the ones, those red objects are sort of the same year, but just a selection of them. We pick the ones that we thought were galaxies, and then we were able to confirm that. And then the last ingredient is to make sure that they're actually relics, so that they're actually as old as the universe. And the only way to do that is to compute their ages. So we really needed to compute the age of a galaxy. We've been doing it with INSPIRE, which stands for Investigate Stellar Population in Relics. And as I said before, this has been a long journey. We started off in 2019, where we were lucky, but also good enough to get awarded a large program at the European Southern Observatory. Those are legacy programs that get a lot of data at the telescope. Telescope data is as precious as money for astronomers. Indeed, there's a money value put there. And in order to get a proposal with, let's say, 8 hours observation approved, you really have to do a good job and to convey the message that your idea is the successful one. The subscription rate is really high. So getting a large program was a great deal for us. We got 145 hours to follow up only 52 objects, but they were the most promising candidates, and indeed 38 turned out to be Relic. And the goals of the projects were to obtain incredibly good signals on those objects, spectra. I'll tell you why we need spectra in a while, to constrain the stellar population parameters, age and metallicity, with the common understanding that metallicity is everything that is not hydrogen for us. And the main purpose was to separate them in younger ultra-compact massive galaxies and relics, because we were really after the fossil records of the first universe. We were very successful in assembling the largest catalog of relics in the universe, and we aim to use them also to sort of inform the simulations and to indirectly measure the size growth phase. Because imagine that if you have, say, if merger is more probable of less probable, then you will end up having a larger or a smaller number of relics at any cosmic time. So if we're able to count relics at any cosmic time, then we can go to the simulators and say, look, you're predicting too many mergers in your simulations. There shouldn't be relics, but we are observing them. So go back to your modeling, go back to your hydrodynamical codes, go back to your supercomputer, rerun things in order to match the numbers that we find with through observations. This is the sample. I know they're not pretty images, but as I said, this is ground-based data, and the galaxies are simply too small to be beautiful. You can imagine that the effective radii, so half of a galaxy, fits within 1 pixel of the detector. They are tiny, they're really incredibly small. So there's no way we can get resolved internal structure, get beautiful picture of them. They will always look a bit boring, reddish, smaller, and some of them are a bit elongated, some of them are a bit roundish, but you know, this is the best we can do. It's a couple of pixels observation, and we can do better from space or with a new technique that I'll describe if I get to the end without anybody falling asleep. Okay, so we said we need to compute ages. But there is a problem here, because we're dealing with external galaxies. They're far, far, far away. And unfortunately, in this case, we do not really resolve single stars. You can look at the picture on the left, which is showing the small Magellanic Cloud. This is a fuzzy nebula on the sky that at the moment the Milky Way is actually eating, so it's falling on us. And it's relatively small inside, and it's incredibly nearby, 200 light years. And here you see single stars in the image. So you can just count them. And this is M87. It's much further away, although it's behind the corner, so it's a local galaxy. It's much, 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 much bigger, or bigger and heavier. So it contains 2 times 10 to the 12 solar masses. It's perhaps the biggest galaxy, the most massive galaxies we have in the local universe. It's clearly an elliptical galaxy, but there's no way we can count galaxy. The only thing we see is a bucket of light coming from the galaxy itself that encapsulates all the stars that are composing this galaxy. How do we do? Well, we can use spectroscopy. You have your favorite system, you can have a spiral, you can have, well, same story with a spiral, there's no way you can see the single stars. You have your favorite galaxy, you pass it through a prisma, the prisma disperses its light, and it gives you in output a spectra. The spectra can have emission lines, so it simply decomposes the light in the different wavelengths, so in the different frequencies. The spectra can have emission lights if this is gas emitting that particular element, or can have absorption lines if this is light coming from the stars that are absorbing a particular element. So you'll see the dip for stars, and you'll see an emission for newly formed stars and gas. Okay, so in a sense, emission is for gas and new stars, and absorption is for older stars. And you also see another big difference, which is the continuum shape. This is becoming brighter towards redder wavelength, and this is staying flat, and it's actually a bit more luminous towards greenish here. Okay, so you already see a huge difference when you get the spectra of two different type of galaxies. And this is shown even further in this slide, where just focus on the upper panel. Here the age is of 10 mega years, and then if I move, and here is redder wavelength and bluer wavelength. If I move and bring the age up to 10 giga year, then you will see the spectrum becoming, let's say, redder and redder, or kicking in the red and in the red. However, if you really look carefully, by the time you reach 1 giga year, the spectrum doesn't change that much. It only has absorption lines, and it looks very similar. So it's not like by looking by eye at the spectra, we can assess the age of a galaxy. We can say if it's oldish or youngish, but it's not like, you know, super easy to tell the difference. Here in this slide, it's quite easy. This bluish object as a spectrum, that point that is strongest in the blue, and then it goes down for a larger wavelength. And this one, which is a very red object, is a fainter year, and then it goes up. But once again, this could be 3 giga years, 5 giga years, 7 giga years. Remember that for relics, we need them to be as old as the universe. So we really need to be able to be more precise on that estimate of the age. Can we do that? Yes, we can. A bit of modeling is required, but we still can. This is a spectrum of an oldish galaxy. Spoiler alert, this is a relic. This is a spectrum of a galaxy, and we can identify in the spectrum some features, some absorption lines that are really age dependent. So they will change in strength as we change the age of the overall population. And by the way, when I say the overall population, I mean all stars that are composing the galaxy. And what we do practically is using models of what we call a single stellar population. So we take a bunch of stars that have been formed during the same collapse of the same cloud. So they all have the same age, and they all have the same metallicity that we know a priori. And then we take a lot of single stellar population models, and we combine them together. And the overall age will be the weighted by luminosity or by mass average of the ages of the various models. Okay, so we take a combination of stars and we combine them together in order to reproduce the galaxy spectrum. And what we actually reproduce is the strength of those absorption lines that are very dependent on age. Then there are others that are dependent on metals, and we can also even prove individual elements if our spectrum is good enough. So this is a zoom in, and that's exactly what I was describing a second ago. You barely see the black galaxy spectrum underneath, but this red line is the fit of the single stellar population templates that I used. Let's assume that I'm using for this particular bit 3 different models. One has a population of 6 giga years, one has a population of 8 giga years, and the third one has a population of 10 giga years, and they all been used 33% for the fit. Then the overall population will have an age of 8 with a spread of plus minus, what did I say, 2, if I remember correctly the numbers. Okay, so we just build up our galaxy by summing together models of stars for which we know the age. If we do that across the entire spectrum, we can have something that looks like that. And once again, red is the fit of the single stellar population models that I'm using, and underneath black is the spectrum of the galaxy. You might see some regions that are less well fitted than others, but these could also have some other source, like bad pixels in my detectors, cosmic rays, bad subtraction of the sky. So obviously when I'm observing a galaxy, there's a lot of sky between me and the galaxy, and the sky itself has some lines, has some tracers. And what we do again is taking a collection of simple stellar populations for which we know the age, and therefore we then build a weighted average. So you have the weights here is the light fraction of that given model, and this is an age metallicity plot, density plot, where I'm plotting the sort of all the single stellar populations that I've used, weighted by light. So here this is the major constituent of this galaxy. It has the largest weight, the highest weight. It's a population of, say, 9.2 in log age, and metal rich. 0 is our sun, so that would be metal richer than the sun. And then the FIT is also using all these models around. That means that there was an episode of star formation, let's say, that lasted 0.5 in log age and produced a spread in metallicity. Before this galaxy, there's a second population of stars that are obviously younger, and they have even a larger spread in metallicity. So this is a nice confirmation of the two-phase formation scenario. This galaxy had a first burst very early on in time. It formed a large amount of its stars, but then there was a second episode of star formation. And as you can see, we don't see the single episodes in the spectra. We just get a spectrum that is the integrated view, and we are smart enough or good enough in our modeling to be able to sort of disentangle between those populations. Okay, obviously with some errors, and obviously that requires very good data. So we really need to apply for the best telescopes. Okay, we did that. We were lucky enough to have amazing spectra. So let me show what happened with 3 examples of the 52 objects that are part of the INSPIRE sample. Starting from the left, this is exactly on the bottom line, you have exactly the same plots that I was showing you before. So age, metallicity, light fraction. These objects has only one population of stars. There's nothing else really. And this population of stars is as old as the universe, or almost as old as the universe. And if you then reconstruct what is called the star formation history, so the percentage of stellar mass that was formed in time from the Big Bang until today, and today changes slightly from galaxy to galaxies because those galaxies have slightly different distances from us, so the light takes a bit longer to travel, then you'll see that this galaxy was amazingly fast. It formed 10 to the 11 solar masses in less than 2 gigayears from the Big Bang. And then it did absolutely nothing. 100% of the stars were in place immediately after the Big Bang. Boom. And then it did absolutely nothing thereafter. The middle one is this is an extreme relic, the most extreme of the sample, in fact. The middle one is still, it depends on your classification. It depends how strict you want to be. But the middle one is still an interesting object because it still has the great majority of its stars that were formed early on in time. In fact, more than 75% of the mass was in place by redshift 2, which is the arbitrary number we're using to split between the first phase and the second phase of the formation scenario. So it's still relic-like, but less extreme than the first, because it has a couple of clouds of newly formed stars. So though you see, this is as old as the first one. So it's just a difference in metallicity. Maybe they come from different clouds, but they collapsed at the same time, very, very early on in time. Whereas this is younger, and so it's a later on stage of the evolution. And then take this guy over here. This is obviously not a relics. It has a lot of stars that are younger. It has still some percentage, let's say between 25 and 50% of the mass formed early on, but then it went through a lot of other bursts. Okay, so this is not a relic, a fossil record of the ancient universe. This is the most extreme one. And now look at the picture. Those are real images taken from a fairly good telescope. It's one of the best ground-based survey. It's called the kilodegree survey. And they're identical. I don't think you can tell that this is a relic and this is not. So that's why my main result so far is that spectroscopy is a powerful and necessary tool in order to identify relics. If you just take imaging, you take a pretty image of a galaxy, you will never be able to tell. You can tell that they're smaller, you can tell that they are reddish, you can tell they're not forming stars, but the star formation history that they went through is essentially completely different in the left and rightmost case. This being said, does star formation work always the same way at different cosmic epochs? I told you a beautiful story. I demonstrated that we can find relics if we're lucky and good enough to get spectra and model them properly. But let's start over. Let's start with our clouds of gas and dark matter that get smaller and smaller because of gravity, and at some point fuel, the critical density is reached and we form stars. This is Alex Cameron representation of stars. Beautiful one, and I must thank him publicly for those animations in those slides, made this morning, by the way, during breakfast. Obviously, when you form a star, you can form it more massive, less massive. Not all stars are just like our sun. You have smaller ones that we call dwarf stars. You have bigger giant stars. And in this particular picture, the small ones are the red one and the big ones are the blue ones. I don't know why. Well, I do know why I chose this color, because once again, blue means star forming and red means old. Okay, keep that in mind. Okay, so counting stars in the Milky Way, we realized there's actually a distribution in the number of stars per unit of mass. Okay, so a given cloud that collapses doesn't form random number of stars per unit of mass, but they follow this distribution, which was assumed to be a power law by Salpeter in 1963, but then it turns out it's a broken power law. You can barely see the broken point. But basically, whenever a galaxy will form stars, it will form it following an initial mass function, which is nothing else than the number of stars formed at any given mass. And this is super important because the mass of a star determines fully its evolution pattern. Very massive stars are the quickest one to die, whereas small stars will live forever. Okay, very massive stars will emit like crazy, will be incredibly blue at the beginning, and then they will very quickly die, contaminating the interstellar mediums with metals. Dwarf stars will stay there for longer time, but because they are many, they contribute mainly to the mass. Okay, but we do not observe mass, we observe light. So am I cheating? Am I able to actually counting star even though indirectly, even though I cannot resolve? Does it make a difference given that stars with different masses are living for different cosmic times? Yes, it does, a huge one. In fact, this is more or less what happens when you weight them by mass. Because there's a huge numbers of dwarf stars with masses below our sun, they will weight the same as more massive ones, okay? You have 100 stars of one mass and you have only one star of 100 mass. They sort of weight the same in this initial mass function that was assumed to be the one that Salpeter computed for the Milky Way. And by the way, every single model in the last, say between the 1916 and maybe 2011 was assuming a universal initial mass function. The only system in which we measured it was the Milky Way. There's no theoretical reason, no physical reason to assume it's universal, but everybody did it. It took me 10 years to convince my colleagues that it's actually not the case. If you weight them by luminosity, then you'll be completely outshined by the giant ones. There's no way you can see the dwarf stars observing the light, okay? Unless you're observing something that has been evolving for 10 gigayears. If you're observing something that is incredibly old, then all those massive stars, well, okay, sorry, forgot to mention that JWST is actually observing those kind of systems. So when JWST observed galaxies at redshift of 10, redshift of 11, when the universe was 5 million years old, so 0.5 gigayears old, then the only stars that JWST is seeing in the galaxy are the massive ones. Okay, because they completely outshine the small ones. The small ones are still being formed following that distribution that I showed you a while ago. So there's gonna be still a lot of dwarf stars. You just don't see them because if you weight by luminosity, sorry, I'm going back. if you weight by if you weight by luminosity, then the giant ones are way more luminous than the dwarf ones. So JWST is sort of observing that side of the initial mass function. With relics that have stars as old, that have been living forever and arrived until today, all those bright stars are dead. Because I told you that the massive ones are the quick ones to be done. They're dead, they polluted the interstellar medium, but then if we don't have the luminosity from those giant stars, we have hope to measure the number or to model the dwarf ones. So what I'm trying to say is that I'm observing exactly the same object, but I let it evolve for 10 gigayears until almost today. And by doing so, my objects are fully complementary to the ones observed with JWST today. They are looking at the giant stars on the initial mass function. We are looking at the dwarf stars in the initial mass function of the same objects, we believe. So those are the predecessor of my relics, and they are the descendants of those objects. With the only caveat that usually those ones will go through the second phase of the formation evolution, and so they will be contaminated by other systems, they'll merge, they'll interact, and so they will lose the predicting power on the very early on phase, whereas they did not. And so they can still inform us on the very early universe, although they are nearby. Okay, so what did we find? JWST sort of revolutionized the field because it looks like they're finding a lot more of giant stars that were predicted by Salpeter in the power law. We found a lot more dwarfs that predicted by the power law. So now we are sort of in the process of telling our simulators friends that they will redo the entire universe, resimulate the entire universe from scratch, and any single model of galaxy evolution and formation built in the last 50 years have used the power law. And now it seems like this is really recent stuff. So if you ask another colleague, they will not be convinced this is true. But it seems like observations are driving us towards a completely different picture, where galaxies are forming following different initial mass function, so forming different numbers of stars per unit of mass, depending on the cosmic epoch of the bulk of star formation. And what I'm trying to convince my colleagues of is that the initial mass function is a ill-defined quantity, because we're not observing the initial condition of a galaxy. As I showed you in the last slide, I am not observing the initial mass function. I'm observing the today mass function. After all this bit is dead already. And please notice that this is a logarithmic scale. So I'm observing a very tiny little part of the mass function, which is by far not initial. And the same is valid for them. They are observing something from JWST. They're observing something that is closer to initial, but they're completely outshined by the massive stuff. So nobody can observe the entire range in mass. We'll never be able to. It's simply impossible because of the mass-luminosity relation. Dwarf stars are giving a lot of contribution to the mass, but they only add tiny little percent in light. This being said, I think I'm going over time, but I promise this is my last slide. Well, I'll skip this one. I'll just show you a pretty picture of a relic taken from this new technique, which is called adaptive optic, and allows us to compensate away from ground, but it compensates the movement of the atmosphere. It's super cool, and it reaches much, much higher resolution, images with much higher resolution, and I really hope you can appreciate the difference between normal and adaptive optic telescopes. And then finally, what is next? Euclid just started to collect observations. We're going towards the internal first data release, and this is what INSPIRE has been collecting so far, and this is what Euclid will deliver. So we'll be able to increase the number of relics of at least a factor of 1,000, and we'll go as up as redshift of 2, which is roughly when the universe was 25% of the age today, and that would allow us to sort of bridge the gap between the local universe and the high redshift universe to also understand how galaxy evolved through cosmic time. And that's it. Thank you, guys, and sorry for taking too much of your time.
Time, 5 minutes maybe to take some questions. So are there any questions?
You want to go?
I have a short one, but not very serious. Why are they called red nuggets?
Oh, well, no idea. This comes from Ivana Damjanov, a very good friend of mine. And they are red, they are small. You see the beautiful logo that we could build up by calling them red nuggets. So it's just because they look like chicken nuggets.
We're hungry.
Oh, we're always hungry. At night at the telescope, yes. Either I convince them all or they are all sleeping.
If not, if you're too intimidated to speak up, you can always come here. Okay, cool.
It's like a very simple part of the travel description, just in the general. It's probably not just really relevant to astronomy, but like science. How do scientists cope with the fact that what they've long held firmly believed is all of a sudden changed by new data and observations or experiments?
50% of scientists are super excited whenever something new and unexpected comes across. 50% of them are super depressed because they realize they were all wrong from the beginning. I think I belong to both classes. During my PhD thesis, I claimed that the IMF was not universal, and I thought this was related to the motion of stars, in particular to the unordered motion of the stars. And I wrote a beautiful chapter, and I got beautiful data to demonstrate that. I did. There's a relation between the IMF slope, so the slope of this power law, and the velocity dispersion, which is measuring the unordered motion of stars. This was, I think, in 2013, maybe, or 2014. And then I, myself, discovered that that's not a real relation. So at first, I was super excited because my new set of data was telling me something unexpected. But then I realized where the data was bringing me, and I was like, oh, I should rewrite my PhD thesis. So there's no simple answer to your question. I guess it really depends on the personality, but this comes with a job. You know, if there's nothing to discover, or if we know everything already, why do we do science for? In a very philosophical way.
So I guess if you have more questions, please come forward, and then we can pack up, and then yeah, hope everyone has a nice evening and
enjoy the cold.
Let's give a round of applause.
Thanks.